Sure. Thank you very much, Sami, for your generous introduction. And thank you, everyone, for attending this talk today. I'm indeed very pleased to be able to be in front of you to present this talk. And thank you, IEEE, everyone, the IEEE staff and local ComSoc volunteers. I thank you, everyone. So this talk is about machine learning and wireless communications. You all know, like, machine learning has emerged as a very popular kind of a topic, right, of research for wireless engineers, for wireless researchers. So basically, what I will try to do here, give you kind of an idea about what kind of problems in wireless communications and networks you may be able to address using machine learning, more specifically using what we call deep learning and deep reinforcement learning techniques. So is it just a hype, or is indeed, there are some problems that can be solved using machine learning? So that's kind of the question that I will try to answer. So anyways, I will start off with a brief introduction about wireless systems, actually cellular wireless systems. We are talking about 5G, but 5G is already kind of, in the deployment, I should say, stage, and researchers are working on beyond 5G and 6G systems. So how are these systems evolving? So to give you kind of a high-level idea, and then I will give a introduction, like a tutorial, you can say, about these neural networks, deep neural networks, and deep learning. It's very brief, very high level, I should say. And also I will talk about reinforcement learning, which is a part of like a category of machine learning. And then I will try to give an example, like where we use this supervised deep learning and deep reinforcement learning technique to solve some resource allocation problem in cellular wireless systems. So you'll probably get kind of an idea, like what kind of problems you can think of solving using machine learning. And if we have time, I'll talk a little bit about the open issues like research directions. So you probably all know, like these cellular wireless networks have evolved from these first generation homogeneous system to kind of a heterogeneous multi-tier, 4G system, and then now we are talking about 5G systems. Mainly, what I can say, like millimeter wave communications and receive MIMO. There have been basically two major kind of enhancements over 4G, which we call 5G, actually. And now we have started thinking about beyond 5G systems, and there'll be new technologies that will, basically will add to the existing, 5G systems. I mean, 4G and 5G systems, and these include technologies like self-remissive MIMO, visible light communications, drone-aided communications.
Professor,
yeah.
Professor, the slides are not moving. One of the.
Oh no, I'm still in slide number 3. I'm not. Yeah, you can see slide number 3. Yeah.
No,
I'm still there.
No, still we are. I think on the first slide.
Oh no. Okay, so why is that? I mean, okay, I'm moving my slides here.
Okay, Cindy, can you help us there? There's a synchronizing something.
You see, like I'm moving now.
Try to unshare and share again.
Okay, sure. Sorry about that. So stop sharing. I don't know how to.
And then I think you may need to make him assign privilege to share again.
Cindy, I don't see like how to stop sharing here. Do you know, like here more options?
Okay, I gave him all the rights, Cindy.
Okay, and also there's an option in the upper right corner to view the thumbnails, to view like all the slides on the side. And if you click on number 3, that might help you as well.
Side-by-side view. Oh, this is, I think, the participant.
Okay, what is everyone seeing now?
No, it's in the first slide. On.
It's the first slide?
Professor, if you like, I can change the slides for you if you like.
Okay. So now you see 2, slide 2?
2,
no?
yeah.
Yes.
Okay.
Slide 3?
3, okay, 3, slide
Yes.
3.
Yeah. So I think it's good. It's working now, I guess.
I'm doing the changing, Professor. So if you like, just let me know.
So, let's try. Okay. Do you see 4 now?
No.
Oh, okay. Then, well, I'm sorry about that. I don't know what's going on.
Okay. So I'll do
Okay,
the changes,
I can dictate and you can move. Okay. Yeah. So, folks, so what I was talking about is evolution of 5G systems. So
slide 3, Professor.
Slide 3 now.
Okay.
So in beyond 5G systems, there may be new technologies like self-remissive MIMO, visible light communications, drone-aided, communications like integrated terrestrial and non-terrestrial wireless systems. And also, as you may already know, there is a kind of a close connection between communications and computing. Things like edge computing, mobile edge computing, they are becoming part of the radio access network, right? So slide 4, please, Sami. So to summarize, basically the networks are evolving toward what we call Internet of Everything, and there'll be a convergence between terrestrial and non-terrestrial communication systems. Of course, as always, we look for more capacity, massive connectivity, large number of devices should be able to connect simultaneously, right? And of course, energy efficiency. And another very important aspect which is becoming, significant is programmability of the radio environment. Like you might have heard about this reconfigurable reflecting surfaces, or some people call IRS. So those kind of technologies will also, evolve, and that will enable us to even program the propagation, so we may be able to program our propagation environment the way we want, right? So that will be also important. So this is in addition to programmability of the network itself, like at the network level, which you call, software-defined networking and things like that. But that's more at the physical level, using IRS and, meta surfaces, etc. And as I was just indicating, the convergence of communications and computing, right? So computing will be part of the communication edge, like access network, like edge computing, fog computing, those things will be important. And softwareization of the network is already, have been discussed a lot, and there is a lot of research on network slicing, like sharing network resources among multiple operators, virtualization of the network resources, and SDNization, kind of for more flexibility, etc. So these are some of the kind of features that we will see in future generation networks. So anyway, so as you can see, things are kind of getting more complex, right? Compared to traditional systems, there'll be a lot of different access networks, right? So different kinds of users, different requirements. So network management and control will be definitely, more challenging than in traditional systems. Slide 5, please. So in this context, machine learning or artificial intelligence kind of is emerging as a enabling technology to kind of solve some of the decision and control problems in networks, right? So people have started talking about these AI-based super intelligent radio access network for 6G. So the traditional problems still exist, but probably with a higher dimension, like with more difficulty, like resource allocation problem, radio design, network personalization. So these are like classical problems that that we have in wireless networks, but there will be kind of more difficulty because, for example, in resource allocation, we may need to talk about allocation of both communication resources and computing resources. As I was mentioning, when you talk about edge computing, the edge servers part of the radio access network, the resources in the edge servers need to be also allocated, managed properly, right? Virtualization of the infrastructure resources need to be done. So allocation problems, resource allocation problems will be more challenging, And traditionally, the way we do, for example, resource allocation and network management is by doing some optimization, right? We generally formulate these problems and optimization problems and then try to solve it. Of course, if you can solve by exhaustive search, that's very good. If it's not too costly, right? And there are suboptimal algorithms like genetic algorithms. And if you have a combinatorial problem, generally we use, again, some suboptimal approaches, greedy approaches, branch and bound techniques, etc. But in many cases, these problems, when you, use realistic assumptions, they are very complex, actually. They incur, high computational complexity. And what it means then, in practice, you may not be able to actually use those methods, because if it takes hours, to solve a problem, then you can use it online, like where you need to solve these problems in each transmission slot or in each transmission interval, right? So computation becomes a kind of a big issue there. If you could solve them online, that would be fantastic, and that's what would be desirable. Next slide, please. So when you have a problem, you cannot solve it optimally, because the complexity is huge. Generally, you look for suboptimal solutions, right? You relax some of the assumptions, right? Use some heuristic algorithm, etc. But then, you at the end you obtain some suboptimal solution. You are not actually solving the original problem. And again, even obtaining the suboptimal solution may not be very easy. It may still have, a lot of computations involved, and also there could be signaling overhead, etc. And the solutions could be far from optimal solutions, and the optimality gap could be unknown, right? So this is how we do things these days, right? And as I said, if you could find a way to solve these kind of problems, right, quickly, with less effort, so that we can implement them online, that would be really, very, very desirable, right? Okay, so next slide, please. So here comes actually machine learning or artificial intelligence, where, we can use some data-driven approaches, actually. So, if many of the problems actually is more like trying to understand the pattern, Say, if I give you an example, say even an optimization problem, right? So, you give some input and you want some output, right? So, for a problem, you have some given input parameters, and there are some optimization variables that you want to find out, right? So if you have many, you have some data, for example, like you have solved this problem, some way, some offline method, and you have gathered some data, right? Where basically you have these inputs and you have the outputs. So these data, if you can understand the pattern in the mapping there, because from the input to output there is a mapping, right? So if you can somehow estimate or somehow approximate this mapping, right, then you can basically solve this optimization online. So what I'm trying to say, from your offline data, say you have solved this optimization using some high performance computers, offline, right? and you have gathered some kind of a sample data. And from that data, you basically understand the pattern, I mean, the mapping, right, from input to output. So basically, if you use the ML terminology, through training, right, through a training process, you understand this mapping. And then after you have understood the mapping, then it's just evaluation of a function, right? So when you apply this system online, then each time you need a decision, you basically evaluate that function. So you see, so you can apply the solution online. You don't need to solve the optimization like every time, which may take hours, right? So this is kind of the essence of using data-driven machine learning, where assuming that you have some good data, right? You use those data to basically train a machine, and training here is simply understanding that mapping from input to output, right? So after you have kind of approximated or come up with a good mapping, then you use that mapping actually for your actual system. So each time you need a solution, every slot, 5 milliseconds, 10 milliseconds, you just evaluate that function, right? So that's what actually the main concept, I should say, idea of data-driven machine learning. So anyway, so machine learning, at a very basic, basic term, I mean, this is understanding relationship between input and output. You have got some data, right? So you want to understand the relationship between input and output. For example, this is the slide I show here. This is about classification of text documents, right? So say you want a computer to classify automatically, right? Some text documents. It could be a home page or different kinds of pages, right? So the input to the computer will be, I give the computer a document and I ask it to classify it. What kind of document is this, right? So again, you see this kind of a mapping, right? There's an input, there's an output. Now, if I have got some test, like a sample documents, I can use those to train the computer first, right? So it kind of learns the mapping, and then after it is trained, then it can basically work. It can start working, right? So now the difference with, like, if you see, we do not have a kind of an exact relationship. Like, you don't know all the rules so that we can write a long program like 100,000 lines if then else statements, right? I mean, to solve this problem. So this is not the case. So we are unable to write a program to actually classify the document, like by using a bunch of if then else statements. So the rules are not known here, So machine learning comes into play when the rules are not known. We got to so we have to use some other way. We cannot use just a normal programming kind of, to solve this problem. Next slide, please. Yeah, so as I was saying, so the whole kind of concept of data-driven machine learning is to develop actually two modules, right? One is the training module, one is the classification module. So you need to have some training data. So the training data is used to train your machine, right? The training module in your machine. And after it's trained, then basically you put your test data, right? And it will tell you the output. Like in our example, right, that we just gave for text classification. So say you have got 5,000 sample documents. So you first use them to train the machine. Now, how to train them, we will see later. So it kind of learns the relationship, and then after it's trained, I give it a sample, I mean, a test document outside those training samples, right? And the machine should be able to tell us the output, So now the performance of the machine will be, of course, dependent on like the accuracy, right? So during the testing phase, I give it 100 documents, and it can classify 90 of them, correctly. Then it's like a performance. You can say accuracy 90%. So it's simple to measure the performance. Next slide, please. So again, as I just said, with machine learning, the solutions are learned by exploiting the data samples. So through this training process, right? So, or in other words, by learning this mapping between the input and output. And as far as communication systems are concerned, as I already mentioned, many of these resource management problems, control and like decision problems can be solved. I mean, as long as we have data, that we can use to train a machine, right? So we can solve these problems online, so that, they become practically feasible, right? Online. Now, deep learning is a class of machine learning which is based on deep neural networks. Now, you see, machine learning is not new at all. It has been there for like decades, right? And it has been used in classical applications like image processing and computer vision, for like decades. But recently, as I was mentioning at the beginning, it has got sort of a lot of attention, and it is being used in many different disciplines. And people are using more what they call deep learning instead of classical machine learning. So deep learning is what the hype now actually, and this is simply based on neural networks. So there are a lot of classical machine learning techniques, but when we talk about deep learning, this is actually about neural networks, and more specifically what they call deep neural networks. It's actually a multi-layer neural network. Again, this is used basically to learn the mapping again. So you use a neural network to learn the mapping between input and output, right? So of course, you can use a training process that what we call supervised deep learning. Now, in many cases, it's not possible, or it's quite difficult to obtain data samples to training. For training, in that case, you use what is called reinforcement learning and deep reinforcement learning. So I will touch on these two topics actually briefly in this talk. Okay, next slide, please. Yeah, so when you want to solve like a resource management or network management problem using machine learning, there is no performance guarantee, because you see, you are trying to kind of learn the mapping. I mean, the mapping may not be the exact. I mean, it's not, may not be able to exactly map, or, the mapping that you learn from your training samples may not generalize to any input sample outside the training set. I mean, so there is actually a performance guarantee. So what you can say, at the end, you again get some suboptimal performance, right? But maybe, hopefully, that suboptimal performance is not bad. It's like an 80% of what you could really achieve in a gene-aided, system. So that's still good. And again, you see, the main motivation is you can use the solution online. You can use it in a practical system in an online manner. So also there is sometimes lack of interpretability. So the mapping, right, from input to output, sometimes it's hard to explain very precisely, right? It works. I mean, but if someone is very curious, why a specific kind of output is appearing, maybe it's not easy to describe. So there is a kind of a black box nature in this kind of system, so that some people may not like it. And of course, if you are using data-driven machine learning, you need data. I mean, training data, right? So it should be, I call them good data to basically train the machine, right? So I mean, so these are the features that you need to keep in mind, right? When you are thinking about using machine learning. Next slide, please. So now, when to use machine learning? So two cases here. First of all, there is no mathematical model. Say sometimes say, for example, you are dealing with a signal decoding problem, for a system where the communication environment is very weird, it's like a very unusual, atypical communication scenario, there is no mathematical model, to describe the, propagation, model, like the environment maybe. So what you can do, you can resort to a data-driven approach. Basically, you generate some training data, like you send something and you see what is observed as output. So basically, so these would be your sample data, right? So you collect those sample data by your experiment, right? You send something and you receive and what was sent, right? So the input-output mapping here. So use these samples to train a machine, and then basically when you deploy the system in a practical environment, then basically based on the training, the machine may be able to classify your received symbols, right? So this is, I should say, one approach to detect signals or decode signals based on a data-driven approach, where no mathematical model exists for the system. It's not like a Gaussian channel or something like that. So you don't know exactly like what kind of decision rule has to be used, right? So you resort to a data-driven approach. Okay. And the second case is there is an efficient algorithm to solve a problem. So again, it is more like a resource management type of problem where you know the problem, you can formulate the problem, but solving it is very difficult because it could be a combinatorial optimization problem, so which is huge, right? You cannot solve it like instantly, right? Only option you may have is to solve it suboptimally, right? Again, your suboptimal solution could be very poor, it could be far from the optimal solution. So that is a case which is called like algorithmic deficit. So then, it's justifiable kind of try to use an ML approach to solve this kind of problems, right? So, of course, when you are trying to solve this problem, so as I said many times, so it's actually trying to learn a function that maps inputs to the output. So you need to be able to formulate, come up with the system model where you know exactly what are the inputs of the system and what you need, like for an optimization problem, right? So it's a constraint optimization problem. You have some objective functions, some constraints, right? Now you're basically trying to solve it using machine learning. By the way, in machine learning community, they call it end-to-end learning. So you have some given values, right? And you have some optimization variables, which are kind of unknown. So basically, those given variables, they go at the input, and at the output, you get the values of the optimization variables. So you need to clearly understand what are the inputs and what are the outputs. I'll show an example afterwards, which will probably make it a bit more clear. The function does not change rapidly over time. Yeah, so if we are trying to learn a function, the mapping, and as I think understandable, if the function is changing rapidly, then it's hard to learn it, right? Accurately. So of course you need large data sets, and as we already said, because the solution is going to be suboptimal, you should be happy to tolerate some error, right? You cannot expect that you will get optimal, like globally optimal kind of performance, right? So as long as you can tolerate some errors, then you can use this approach. Next slide, please. Okay, so I give a simple example here for a resource allocation problem. This is a kind of very typical, like a channel and power allocation in a multi-cell network. Say you have got K cells, right, cellular system, you've got F channels, right? Bandwidth of each channel is B, and each cell allocates power to each of the channels that it uses, right? We are talking about downlink transmission. So we assume a discrete power level, right, for each channel. And each base station has a limit on the maximum amount of power that it can transmit in the downlink, right? So this is the constant. So the total amount of power transmitted in the downlink across all the channels, right, is limited by this value here. So what is the problem here? So we have a bunch of channels. We got a bunch of base stations, right? And of course we have a lot of users, right? And we have power that we will use in the channel. So a typical problem is how to allocate the channels to the users, right? And how much power to allocate in each of the channels. It's like a typical power allocation problem. So we are trying to solve it for a large system. So for example, we have got 100 base stations, right? Generally in typical like a actual system, they'll probably do it on a 2-3 cell or maybe just a single cell. But I mean, if you can solve this for a large system, you'll probably get a better solution, right? I mean, it's like a coordinated solution. Anyway, so how do you formulate this problem? Next slide, please. Yeah, so one way is we want to optimize the total rate in the whole system. Total, transmission rate in the downlink in the whole system. So I think it is not very difficult to see. This is the total rate, if you call it some utility, right? So this is what we want to maximize. Next slide, please. Yeah, so the optimization problem is kind of like this. So you maximize the total rate subject to this power constraint in each base station. So, this is a typical problem, and this is, if you're familiar with, this optimization theory, you can convince yourself this is a non-convex and combinatorial optimization problem. So, I mean, it will have a lot of computation involved if you want to solve it optimally. So I show you a simple example here, like for 15 cells with 5 channels, right? If you just want to solve the power allocation in a truly optimal manner, you have these many possible combinations. I mean, this is infeasible to do, right? And if you want to do both channel and power allocation, this will have these many possibilities that you need to check to find the best one. If you want to do it exhaustively, right, because it's a non-convex, so the global optimal solution can only be obtained by an exhaustive search, which is like in this, even for this kind of a simple system, this is like impossible almost, right? So we have an algorithmic deficit here, right? We know the problem, we can formulate the problem, but solving it is like huge. We can't do it for a practical system, right? So this is a case where you can argue that, well, we can try to use some machine learning technique that makes sense to use. Next slide, please. Okay, another example of this algorithmic deficit, where basically you have this algorithmic difficulty. This is a user association problem, say in an interference channel. So you have got multiple transmitters and multiple receivers, right? And they're all using the same channel, for example, the same transmission channel. So of course, one transmission will interfere with the other, right? Because they're in the same channel. So the question is, you see the users are geographically dispersed, right? So the question is, which users should associate to which transmitter? So maybe, okay, so in this case, assume that all the users are in the coverage of all the transmitters. It's like think of a hotspot maybe, or a lot of access points, right, around, right? So users are all in the, are in the coverage of all the access points. Now the question is who connects to which access point? So user association, right? So which user associates to which access point, so that the total rate in the system can be maximized. So next slide, please. Next. Okay, so this problem again can be formulated as an optimization problem. So you have got K transmitters and receivers. So this is the association variable rho, right? And this is the rate. So the total rate is given by this, and your objective is to maximize the total rate and subject to some constraints here. You can say, okay, one transmitter can only send to one receiver, but one receiver can receive from multiple transmitters. So this is the constraint here, the second constraint. And there is a minimum rate constraint here, okay, for each user. And the association variable is binary, right? So it's whether user K or user M associates to base station K, then it's 1, otherwise it's 0. So again, this is a combinatorial and non-convex problem. You see, these problems are very typical, right? I mean, this is what you want to solve. But you see, when you put it in optimization, I mean, they are very difficult to solve in an optimal manner. So in reality, what you do, you try to somehow convexify the problem and relax some of the assumptions so you can, find some solution, but then they're kind of suboptimal, or they are not actually solving the original problem. So again, you have an algorithmic deficit here, and maybe you can try to use some data-driven approach to solve this problem. So this is also a valid case where you can use machine learning. Next slide, please. Okay, so folks, I think you got kind of an idea, right, about these two concepts here, like a modeling deficit and algorithmic deficit, basically, which tell you like what kind of problems you can attempt to solve using data-driven approaches. So as long as you can fit your problem in one of these two categories, so it makes sense to use machine learning. And as I was saying, machine learning is not new actually. The classical machine learning techniques have been used for wireless communications. You will find papers from 90s, so for different problems, starting with physical layer problems to, even for security, like an application layer, fault detection, security problems. So many of these problems have been, they have used classical machine learning techniques. But these days, people are talking about deep learning, so the focus now is more on deep learning. People don't talk much about these classical techniques, but they talk mostly about deep learning. Next slide, please. So, now I will quickly go through a kind of a tutorial on different machine learning techniques. So machine learning techniques can be categorized into three categories. Supervised learning, unsupervised learning, and reinforcement learning. So supervised learning is what we have been discussing so far. So here we got a data set, right? Given data set, which basically tells you, okay, for this input, this is output, right? So you use this data set to train your machine, right? And to learn that that mapping, right? That approximation, mapping between input and output. And then you basically hope that this mapping will work for data outside the training set. So the better you can train, the better you will be able to generalize. Okay? And now, supervised learning techniques can have outputs which, have discrete output or continuous output. So when you have discrete output, they're like classification problems, right? And when you have continuous outputs, when your F is a mapping, right? When your F generates a continuous value, so it's like a regression problem. When it's a discrete value, then it's called a classification problem. Next slide, please. Next slide, please. So these are the common supervised learning techniques, very classical Bayesian classification, K nearest neighbor, neural networks, support vector machine, decision tree. So yes, these are the classical supervised learning techniques. But since, as I mentioned, we are talking about deep learning, so we will talk about neural networks. So neural networks are the basis of deep learning. Next slide, please. So a neural network is something that looks like this. You got a bunch of neurons. These circles here, they are called, okay, these are the input layers. And then in the hidden layer, you got some neurons. They call them neurons. And then you've got an output layer, again, some neurons. So this is like a fully connected kind of a neural network where, all these neurons are connected, right? To all the hidden layer neurons are connected to all output layer neurons. So, so you can have one or multiple outputs. Like in this case, you have got multiple outputs. You've got multiple inputs. So basically, again, it does a mapping, right? So it maps inputs to outputs. So there is a theorem, basically. What it says, a neural network actually can approximate any function with kind of very good accuracy. I mean, saying high level. So a neural network is simply an approximator. It basically approximates a function. So you've got input and output. So it tries to kind of approximate this input-output relationship. Okay. Next slide, please. Yeah. So now quickly, this is how a neuron looks like. Like neurons are the building blocks, right, of a machine, of a neural network. So a neuron is simply like what it does. It takes these inputs, right, and does a weighted sum of them and adds a bias, right, and then this goes to a activation function, and it could be a linear, non-linear function actually, and then it produces an output. So this is how. So you see. So this is basically again like doing a function, right? I mean, you give a bunch of inputs and it produces an output, right? So it does a non-linear kind of mapping of the inputs to the outputs, and you basically connect many of those neurons together, and at the end, the whole network acts as a function approximator. Next slide, please. Yeah, so there are different kinds of activation functions. I don't go through all of them, but just for information, like sigmoidal, hyperbolic. So they're all like non-linear kind of activation functions. Next slide, please. Next slide. I'll quickly go through an example. Next slide. Next slide, please. Next slide, please. I'll show you this one is a neural network that approximates an exclusive OR function. This exclusive OR, right? The two-input exclusive OR. So just to basically tell you again that a neural network is a function approximator. Now, in this case, this can implement the function exactly. So this is not approximation. This is actual, like a real, perfect implementation of the exclusive OR function. So you need like 3 neurons to approximate this exclusive OR function. And you got these weights, you see these weights, W's, and you've got these biases, right? So the problem is to basically find these values. So as long as you can find proper values for these weights and biases, this will work as a two-input exclusive OR gate, right? So your inputs come from these. And as long as I said, if you can choose these values properly, select these values, W's and biases, then it will implement a two-input exclusive OR function. So this is what a training process does, is actually to find these values. So the training process will be required here to obtain these values, weights and biases. So basically, what are our data? Our data is like this. If you put 0, 0, it should be 0. 0, 1 should be 1. 1, 0 should be 1. 1, 1 should be 0. This is our data, right? This is we know. This is how a two-input exclusive OR gate works. So what we will do, we will initialize these values, W's, with some any arbitrary value, and then we give this data. We put say 0, 0, and we observe what is here. It should be 0, right? But initially it could be something else. So it's not basically trained. I mean, so we need to adjust the values, W's. So the adjustment will be based on the error, like the one that you observe here and our actual output. So this is basically called the loss function. So this is captured in the loss function because we have got 4 inputs, for example. So we get 4 different values, and we know the actual values, right? So the difference, if you take the error square, sum of the error square, average, like basically mean square error, right? So mean square error, that can be our loss function. So what we can do, we can basically minimize this loss function in order to obtain these values. So this is the whole kind of essence of learning in a neural network, right? So from your data, you see when you apply the data, right? What you see what is the output, and you can calculate the square error, right? And then you adjust, and then you do it again, right? And see, you can do it like a multiple iterations. So until you kind of saturate, you cannot improve any further. So this is the whole essence of learning, and the process is basically called backpropagation algorithm they use. Okay, so next slide, please. So, folks, I think you got the basic idea of what is a neural network and what does learning means, right? And how do we learn? So basically, it's a forward propagation and back propagation, right? You give the inputs, and they propagate to the network and produces some output. And from the output, you calculate the loss function, and you basically propagate it back, to adjust your weights, right? So this is back propagation. So they call this kind of neural network like feed forward. I forgot the exact terminology. So feed forward back propagation neural network. Now, when you have more than one hidden layers, they call it a deep neural network. So in a typical network, you have only one, but here you have got more than one. That's called the deep neural network. And in general, I mean what is observed, what has been observed, when you have data has higher dimensionality, it's a high dimensional data, a lot of features, right? A lot of inputs, for example, like then a deep network can provide better accuracy. I mean, intuitively, what you can think of, it can approximate the function better. You make it more complex. Okay, I'm using this term kind of loosely. So you make the network complex. I mean, then it can approximate the function kind of more accurately. That's kind of, high-level explanation. Next slide, please. Okay, so these neural network-based, learning, it of course depends on data, right? You got to have data to train your machine, right? To learn those ways, right? Now, in many cases, maybe you don't have data, right? I mean, it's not possible to even generate those data. Maybe like an optimization problem is a combinatorial. I mean, it may take months, to even generate those data. Years, maybe it's out of question. So what do you do then? So this is another approach which does not require any a priori data. So in this case, the agent learns by interacting with the environment. So, for example, who is an agent here? Agent is the decision maker. Say, for example, the base station or the say SDN controller. If you think about this multi-cell resource allocation problem, maybe there is an SDN controller, right, that is controlling all these 100 base stations, right? And it has to make the decision which base station uses which channel and how much power to allocate in which channel. So you can think of like a cloud RAN kind of a scenario, right? So there is a cloud, there's a server in the cloud, we call it SDN controller or whatever. So it makes the decision, right? So this is the agent, right, who will need to make the decision, but it does so by interacting with the environment. It has not been trained. It does not, nobody has trained the controller because there is no data. So the idea of reinforcement learning is it interacts with the environment. That means it takes a decision and executes it and see what happens. Like for example, in our context, you can say, okay, it makes a decision on the channel and power allocation. It says how much is the total rate, right? So this kind of the reward, right? And based on the reward, it can update its action. It can change another action. It's not only based on the reward, but also the environment might have changed, because with a particular channel power allocation, for example, the user's SINR and things like that will change. So those could be like the state, So by observing the state, it can take another action. So eventually, it may be able to make the optimal decision. You see what I'm saying? So it is like exploring, and exploiting, right? So in a certain state, with a certain, user's SINR and, right? It takes an action. It observes the total rate, for example, that comes as a reward. And also it observes the change in the system state and it takes another action. So it's like it's like making decision by observing the system state. And if you have a good algorithm, maybe you will be able to learn this mapping from state to action, which is the policy, which you call the policy, the optimal policy soon. I mean, hopefully you can develop an algorithm, learning algorithm, so that you can learn this mapping of the policy from state to action quickly, right? So that's the idea of reinforcement learning. Now, next slide, please. I'm just explaining to you folks at a kind of a high level. So generally these decision problems, like a single agent decision problems, they are formulated as what are called MDPs, Markov decision problems. Now, when you formulate a problem, as a Markov decision problem, then you need to know these state transitions. Like in each state, I take an action, it may go to another state, right, with certain probability, another state with certain probability. So these will define a state transition matrix. And I need to know the reward. So when MDP is defined, in terms of all these transition metrics, then you can actually solve using a traditional value iteration, policy iteration technique. But the problem is when you do not have this state transition matrices defined, you don't know them, you don't even have any idea about the reward. Then you actually use reinforcement learning to solve these MDPs. So these decision problems, when they cannot be defined, properly, in terms of these transition matrices and the reward function, you use reinforcement learning, okay? And the most common reinforcement learning technique is what is called the Q learning. So as I said, you basically try to understand or learn the optimal policy, right? In certain state, what is the best action to take, right? So that you can maximize your reward, long-term reward, okay? Next slide, please. So this is, you can think of learning a table, right? So the system can evolve to multiple states, and in each state, you have multiple choices of actions to take from, right? So, and you're trying to learn in certain state, which is the best action to take. So it is like a learning a table, right? It's like a learning this QSA table. It's like a two-dimensional table. The state at the rows, say actions at the columns, for example, right? So you learn by interacting with the environment, right? You see the reward that you get with certain action, right? And then the system moves to a different state, And in that state, you see which is the best action so far based on your table. So for each state action, you have a Q value. This is like the action value function QSA that gives you the value of a certain action in a certain state, right? So you are trying to learn these values over time. Next slide, please. So, and this is the way you update your Q values. When you take an action, you get a reward, and the system moves to a new state, right? Okay, so when it moves to a new state, this is how you update the state value function. Okay, so this is Q learning, and you will see many paper, many words that simply use Q learning, to try to learn the optimal policy. You try like the optimal. For example, I can tell you, say access point selection. Again, user association problem. I mean, you can use a Q learning, right? So okay, a user state could be, say, its delay maybe, or maybe throughput, right? And so each time slot, it can try to select different base stations. These will be like the actions, right? So you've got 5 base stations, so you've got basically 5 different actions, right? So you try to learn these QSA values, like you can think of the reward, right, for taking an action in a certain state. So after a while, probably you will learn your optimal action. Like if you're in this state, state could be a delay, throughput, whatever, and what is your best action. So after you learn it, basically you can use it as like a lookup table. But the point is, in a wireless system, this environment will change. So this may not be valid. I mean, when you learn this best, but in the meantime, the propagation and things may change. So basically, you got to learn again. So this is a problem. Like with using this kind of Q learning, when the environment changes rapidly, then converging to the best policy may not be easy. Okay, so this is kind of an issue. But if the environment is kind of stationary, it will work well. Okay, next slide, please. Okay, so now when your state becomes too many, right, or state is continuous, as you can see, these kind of state action, because we are thinking in terms of a table, right? I mean, that becomes like too huge, or it's kind of not very manageable. So then the idea is to, okay, well, I mean, we are not trying to learn this as A, when S is kind of continuous. Rather, we will use what is called a deep reinforcement learning. Next slide, please. I'll show you a figure which will explain. Next. Yeah. Oh, so here is it shows clearly the difference between Q learning and deep learning. So in Q learning, the agent looks at the state, right, and it finds out what is the best action from the table, right, that it is learning. Basically, QSA values. Any other? So from the state, it looks at the table and find the best action value, right? Now in deep Q learning, basically the agent will look at the state, and the state goes into a neural network, and the neural network will produce these Q values. So for different action, you've got n actions. For each action, it produces the Q value, right? So, and then the agent can decide, okay, which action to take based on this Q value. So maybe the highest one, it will choose to take that action. So it's basically, you can say, approximating the Q values here using a neural network, right? Instead of just like a kind of using a table, kind of a lookup, right? Kind of table is here is using a neural network to approximate the Q values. Okay, so as I said, when your state values are continuous, I mean, then using a table and something like this doesn't make much sense. So you rather use deep Q-learning. Okay, next slide, please. So here I will quickly show you two examples. Okay, so now we have probably some high-level idea, right, about this supervised deep learning. So basically, using a deep neural network to learn this mapping between input and output, and also this deep reinforcement learning, where basically the decision maker, the agent, wants to make a decision by interacting with the environment. We don't talk about any a priori training or data, things like that. So if you go back to our resource allocation problem, multi-cell resource allocation problem, so how do you use this deep supervised learning approach? Next slide, please. So think about this. Say you have got, say, 5 base stations, 5 users per cell, and you have got 3 channels. So, okay, we are first doing this supervised deep learning approach first. So basically, we'll use a deep neural network to solve this optimization problem, and we'll need some training data, right? Basically, those training data will come from the optimization problem, but we need to have some other way to solve this optimization, maybe it's a genetic algorithm or things like that, or some techniques from where we get those data. So you use those data to train our neural network. But the first question is how that neural network looks like. So I'm just showing you how to design the inputs and outputs of the neural network. So you have got 5 base stations, 5 users per cell, and 3 frequency channels. So for each frequency channel, so for each user, there is a channel quality, right, indicator. So there are 3 values for each user. So you have got 5 users, so you'll have like a 15 inputs. Now, in addition to this CQI value, you also use a user's location as also input to the machine. We tell the neural network, okay, these are the users' CQI in the different channels, and this is at the user's locations, and you tell me which user should be allocated which channel and what power to be allocated to which channel. So this is what we are trying to do. So now, in this example, you will have 100 inputs. That's what I'm just showing you, like how many inputs you need to have. So if you know in your system, okay, you have got at most 500 base stations, you can have at most 50 users per cell, and you have 50 channels, so you know how many inputs your neural network will have. Next slide, please. And how do the outputs look like? So your outputs, okay, so for example here, in one base station, in one channel, one cell, we said there are 3 channels, right? So now this shows channel and power allocation. Okay, first the power allocation here. Channel 1 gets power allocation level 1. We said discrete power level, right? So we just label them as 1, 2, 3, whatever. So channel 2 gets power level 1. Channel 3 gets power level 3, right? And subband allocation, channel 1 is allocated to user 3, channel 2 is allocated to user 5, channel 3 is allocated to user 2. You see, so in each cell, you will have like a 6 kind of outputs for each cell. And you know which output means what, right? So the first output, for example, is basically tells you what power goes to channel 1. Now, I mean, you can convert to binary, and also maybe complement binary. So you'll have 36 outputs for each channel, and if you've got each cell, if you've got 5 cells, you've got 180 output. So this is just showing you how you design your neural network, like the inputs and outputs. Now, then things are easy. If you're using some, machine learning platform, like PyTorch or, TensorFlow or even MATLAB, I mean, that's what you get to tell them, you know, how do you define, and everything MATLAB will do it for you. So you basically just define your inputs and outputs, number of layers and things like that in your neural network, and it will do it for you. Next slide, please. Anyway, so in our case, we did like a neural network with 4 hidden layers. Okay, I'm not going into the details, but so the problem was solved using like a neural network, a deep neural network with 4 hidden layers, and you show how many inputs and outputs in this. This shows the inputs and outputs for this hidden layer and how they were done. I mean, the details are in the paper. I mean, you know, due to the time limitation, I cannot explain all of this. Next slide, please.
Excuse me, Professor. I think we have around 15 minutes or 16 minutes.
Yeah. So I'll take a few, probably 5 minutes, and we'll be done. Sorry about that. So next slide, please. So folks, you understand like how we develop this neural network model, right? So now I will show you some performance results. So as I said, we need data, right, to train this neural network. So in this case, we obtain those data using genetic algorithm. Of course, it is done offline, right? Genetic algorithm, and this basically shows the accuracy of the data. Because for a small system, I mean, you can test by exhaustive search as well. I mean, so in this case, the genetic algorithm, the data it provided the optimal solutions. They were like 85% time they were accurate. You know, the accuracy was 85%, and of course, the time it took was quite small compared to the exhaustive search, right? So the data is generated offline using genetic algorithm. Next slide, please. Next slide, please, Sammy. Next slide. Yeah. So this shows some results on the accuracy of the neural network. And, you know, so the number of hidden layers is like a parameter that you can play with. So in this case, 4 was good choice. Now, what I can comment on, this is more a trial and error process. You know, how do you configure the hyperparameters of your neural network? This is like an iterative, you know, approach, trial and error. So there is no recipe for that. I mean, so it depends on the problem, you know, and the data, etc. So you got to use a trial and error approach. Next slide, please. Next slide. Okay, so well, what I probably in the previous slide, Sammy, just say something on comment on the previous slide. So with this supervised DL approach, the accuracy, the test accuracy was 86%. What it means, I mean, when we give a data sample outside the training set, the optimization was solved. You know, the result was optimal, like 86% of the time. So basically, I mean, you know, so it's not it's a suboptimal solution, but you can think of like 86% of the time it is almost like optimal. You know, so or 86 out of 100 results were like optimal. Basically, optimal means like a genetic algorithm. I mean, the result that was obtained by genetic algorithm. So, you know, this is something acceptable. That's what I said. If you are happy with a suboptimal performance, right, not too bad. I mean, then it's feasible to use this approach. Next slide, please. 3 more minutes I will take. Okay, so now the same problem you can do using deep Q learning. You don't have any data. Now this example here only for power allocation. We don't do channel allocation here, just for power allocation. Again, so this is a combinatorial problem, because if you want to do it exhaustively, you need to search through, you know, all these p to the power f different combinations. But if you don't want to do it, so you do a deep reinforcement learning approach. Next slide, please. Next slide. I'll probably, you know, just go through now you use a neural network right here for a deep QL. Now that neural network has to be trained, right? Now, if you recall, this was the Q learning equation. And now, how to update those Q values. I mean, that neural network, simply speaking, that neural network has to be trained, right? I mean, again, using a backpropagation algorithm. So that neural network produces your Q value for the different actions. But now, based on those Q values, you have to define a loss function and use that loss function to update your neural network parameters. But where do you get that actual Q value? So what you do here, if you use an algorithm, what is called the experience replay, basically they use two neural networks. Next slide, please. So one is called prediction network, one is called target network. So basically the Q values that you get from target network, they are used as the actual values so that you can use them to define the loss function and then that propagate to update the values in your prediction network. So, okay, so in one sentence, this algorithm, what is called the DQL with experience replay, this is like a typical algorithm, that works in this way where it uses two neural networks actually. One is prediction network and one is target network, and target network is used to, you can think of like training this prediction network. Next slide. I'm done. I'm just going to the results. Go next, please, Sami. So what we do, we do some tests on this DQL with experience replay. So again, we use a 4-layer neural network, remember, for this DQL. And these are the settings, like the hyperparameters for this setup. Next slide, please. So basically, how do you observe the performance? So we see, what kind of throughput you get, right, over time. Okay, so and the purple one is the one that you get with the result that you get from genetic algorithm, right? And in this DQL, you see, you learn by interacting with the environment. Each time you take an action, you get some throughput, right? So over time, the throughput variation fluctuates like this. And if you average over time, that's what you get. This orange color is basically for the DQL one. So you see, this is superior compared to several other benchmarking schemes where you use random power allocation, or even there's another algorithm, WMMSE. So it actually performs better than this. And the right side basically shows the arrow, just the complement of what is shown on the left side. So the arrow is, the least for this DQL compared to the other algorithm. So the lesson is, if you can configure your DQL properly, with hyperparameter set properly, you can give you a good suboptimal performance. I'm done. Next slide, please. What's the conclusion? Yeah, so, sorry, the previous slide, Sami. So to conclude, AI and machine learning are equitable to address complex wireless problems, as I said, where you have either modeling deficit or algorithmic deficit. It makes sense to try to use some data-driven approach or even a DQL approach. And there are a lot of works currently, being done at basically using mostly this DQL. I think this has become a kind of a popular approach to use DRL to approach some of the complex resource management problem and basically solve some optimization problems. Okay, so but one thing to remember here, the DRL models are very problem specific, and you need to tune the model based on your problem, so there is no like a common recipe. Okay, and we can leverage at the communication researchers, we can leverage many of the state-of-the-art DQL techniques which are developed by the ML community, developed by ML researchers. So there's a challenge in optimal configuration of the DL model, like the hyperparameters optimization, etc. And also newer techniques like distributed reinforcement learning, federated learning, they are also becoming popular, where you want to reduce the computation load maybe in one agent, right? Rather, multiple agents can cooperate to learn in a cooperative fashion. Maybe it will it can improve the convergence and also
Okay, Professor, I have to stop you here and just link that last point. But before that, we have to thank Professor Ekram for this really great talk. It's a deep talk, very dense talk. Thank you, Professor, very much for this wonderful talk and for your time and for your effort. And let me link here the last point that we talked about. We have one question here, and I have to say to the viewers that I have to choose only 2 questions because we have a limited time. So I'm really about that. I really apologize. So is it feasible to use deep learning in a base station from the hardware point of view, or is it only feasible in the clouds because we have strong processors and computers?
Yeah. Well, that's a good question, of course. I mean, now if it is supervised learning, you see, it can be done offline actually. So, I mean, it does not necessarily need to be done in the base station because any offline learning can be done somewhere else, right? So if it is a supervised DL, it can be done in the cloud. It doesn't need to be in the base station. But if it is deep reinforcement learning, then it is presumably it will be in the base station. But then again, as I was mentioning, using techniques such as distributed learning, sharing learning experience among multiple base stations, etc., can make it easier for a base station, so basically reduce the load, you can say, in a base station. But for supervised DL, it can be in the cloud. Yeah.
Okay, so moving to a very basic questions, how to use the activation function in machine learning in general?
Yeah, so that's also a very good question, a technical question. So now there are some issues of using a certain kind of activation functions. For example, sigmoid function, I mean, sometimes, for back propagation, this doesn't work very well, in terms of lining those weight parameters. So people use like other activation functions, like a rectified linear unit and things like that. So it impacts the learning process, and some of the activation functions are preferable to other functions.
Okay, so I think you have to stop.
Yeah, if you can select, then good to trial and error. It depends on the data and things like that. Yeah.
Okay, so I think we have to stop here and wrap it up here. So again, we thank the Professor Ekram Hossain for this wonderful talk. It's very new information for all the community, ComSoc members here and in the region. And I have to thank all the guys that have viewed us here and joined us. And I have to thank the XCOM, Jordan XCOM, and Cindy for her help. Thank you guys very much. And just to remind you, we will send the slides. Professor, if you can email me the slides if you may.
Yeah.
And thank you, Professor. And I will distribute an edited version of this video without me, talking much about the ComSoc, Jordan ComSoc to you guys. And thank you very much. And see you soon. Thank you, Professor.
Thank you very much, folks. Have a good evening. Take care and stay safe. Thank you.
Take care. Thank you, guys.